All right, good morning, everybody. And we are getting ready for our final topic. It might be split up into a couple of chapters, but it's really one topic. And it's the topic of, whoops, differential equations. Our final topic. We are very close to the end. So previously, in high school and earlier perhaps, your initial concept of an equation, your initial understanding of what an equation is, has been something like, let's give something very simple, 2 times x plus 1 equals 7. That could come from a word problem or not, or just made up. You're practicing the algebra, whatever. This is our concept of an equation. So it's a mathematical sentence giving me information about this missing or this mystery number. And the sentence gives me information to find what that missing number is. And then when we solve it, the solution to this equation is a number. More specifically, the value of x. Now, sure, in some equations, maybe like a quadratic equation, you can have more than one option for what this number is, but it's still a number. So that is what we think of when we think of an equation. However, it's not complete. There are other kinds of equations. So I'll leave that. So let's see here, a new kind of equation. And I'm going to give an example. I'm going to say here 1 plus the derivative of y with respect to x equals 2x. This is certainly a mathematical sentence. It has information. It certainly gives me information. But what it's giving me information about is about a function and not about a number, a mystery number, but instead about a function y of x. And I'm trying to find the mystery function y of x. And the information that it gives me is that if I take the number 1 and I add the derivative of the function, I get an answer, so to speak, of 2x. So the sentence topic is different than my original style of equation that gives me information about a number. This one talks about a function. So the solution to this equation is therefore going to be a function. Now that's going to be the function y of x. Now, yes, it depends on the complexity, just like before, where I could have multiple answers, but those answers are all going to be functions. So I have a new kind of equation, and we're going to call that appropriately a differential equation. More specifically, an ordinary differential equation, because you do find, if you pursue this topic further, there are other kinds of differential equations, just like there are different kinds of normal variable, let's say, equations. But that's not a route we're going to take, so we'll just call it a differential equation. The most important thing is to realize what a solution to this equation looks like. So if I take my 2x plus 1 equals 7 versus 1 plus dy dx equals 2x, those are both equations. One is let's call it a variable equation, a number equation, and the right one is a differential equation. If I say a solution to this equation is 3, what does that mean? How do I verify that that is, in fact, a solution? I'm going to calculate the left-hand side by plugging it in to x. And I'll get 2 times 3 plus 1. And then I'm going to, if there is something to calculate or evaluate the right-hand side. And if these two are the same, then yes, it is a solution. The same concept applies to this differential equation, where if I'm given a guess of a potential solution as x squared minus x, that's a 2 there, I can again verify that by evaluating both sides of the equation. The left-hand side is going to be 1 plus the derivative 2x minus 1. The right-hand side is 2x. Remember, I'm not looking at a number value of x. My answers are functions. They are the same. Therefore, yes, it's a solution. So my approach to equations are the same. These equations are the same. My approach is the same. But what I mean by solution is very much not the same. Usual number equation, the solution is a number. Differential equation, the solution is a function in the variable. Okay. To emphasize that further, we're going to look at some problems where we're given a function and we just want to check, is this a solution to the differential equation? To really emphasize, what do I mean by solution? Because it's very important. Even though it's an equation, it's a very different kind of equation. So let's just do number 1, for example. Oh, it doesn't have numbers. The first one, the first dot in 13.1. So 13.1, first dot, I have a function. Nope, I do not have a function. I have a differential equation first. What is it? It is dy dx equals 3 times y. So dy dx, is it negative? Yeah. Negative 3 times y. And I want to verify the function verify the solution function y of x, 2 times e to the negative 3x. 2 times e to the negative 3x. All right. So now I'm going to look at the left-hand side of this equation is dy dx. That is going to require that I take the derivative of my proposed solution. And we know how to do that. The 2 stays in front. It's going to be the chain rule, so the derivative of e to the something times the inside something. I can simplify to negative 6 times e to the negative 3x. Now let's see if the right-hand side simplifies to the exact same thing. Well, the right-hand side is negative 3y. So I put in my proposed y function, 2e to the negative 3x. Simplify that to get exactly the same thing. So yes, it is a solution. So the same concept as equations that we learned quite some time ago in school. Plug it in. Is the left-hand side equal to the right-hand side? If it is, then that is a solution. But now my answers aren't numbers, my answers are functions, both in terms of what a solution is and in terms of what the left-hand side and right-hand side become when I plug in this proposed solution. All right, let's do one more. And let's look at something a little bit more complicated, perhaps. Not much, but just what should we look at? What should we look at? Let's try this one. Let's zoom in on that one. Let's try that one. So that doesn't have a number. My next problem is dy dx equals 4xy, and I'm looking to verify the function y of x equals e to the 4x, All right. So now I go left-hand side, plug it in. Left-hand side requires that I take the derivative, so I will do that on this function. That is going to be 4e to the 4x. Right-hand side requires that I evaluate 4xy. That means 4 times x times the proposed y. So I get 4x e to the 4x. And I see these are not the same. So my y of x function, e to the 4x, is not a solution. Just like if I were to have a basic equation, plugging in a number and the two sides don't equal each other, then that's not a solution. I'm just now working in functions, and then the equations become differential equations. Okay, so there are some similarities, but there's also a bunch of new things. You can then say, okay, well, that wasn't a solution. Great. How do we then find a solution? It's fine if you give me one and it works, But if you give me one and it doesn't work, or you don't give me one, how do I find a solution to a differential equation? Now, in general, that is an extremely complicated question to answer, but for our purposes, we have a fighting chance because we're only going to look at that first step to an answer to this question, which means we're going to keep the differential equations quite basic so that we can get an idea of how this works. And then following that, we'll see a lot of practical problems where even this basic kind of differential equation, this basic approach, gets us a lot of practical answers. So first, let's just look at what we have done so far without realizing it in our antiderivative questions so far. We've done differential equations without realizing it. For example, I could have said, I'm thinking of a function, let's say here, find the antiderivative of, let's keep it super simple, of 2x. What does that mean? What does that mean? That means I'm looking for a function. Let's call it y of x, such that its derivative is 2x. Right? The antiderivative question was the reverse question than the derivative question. Previously, I was given a function, and I need to find the derivative. Now I'm given the answer to a derivative question, which means I am really given a differential equation. This is a differential equation. And by asking for the antiderivative, I'm asking for a solution to this differential equation. And we know a solution is represented, my function y is represented by this indefinite integral, which I can then just reverse engineer my known derivative properties to get x squared plus c. So I see that there are actually a whole bunch of solutions to this differential equation. A whole bunch. I don't know what c they are interested in. So I keep it general, and I call this the general solution to this differential equation. So we've already seen differential equations. We just didn't know to look at it as a solution to an equation. We were just asking antiderivative questions, and then we were naming that answer by way of an indefinite integral. But what we were really doing was solving a differential equation. And the answer that we get is called the general solution. So let's just see in our problems where they're asking for a general solution, how far we can get with this. So if I look at this one, for example, dy dt So now I don't have an x variable, I have a t variable. I'm trying to mix them up because in our practical problems, the independent variable is time, and we'll use a t for that. But the concept doesn't change. dy dt minus e to the 2t. So this is now in 13.2 dy dt minus e to the 2t equals 0. This is a differential equation because it has a derivative in it, which means my answers are going to be functions, this time functions in t. So we're looking for a function in t, function called y, based on this derivative's name, such that this equation is true. But I can rewrite this equation to dy dt equals e to the 2t. That means that what I'm really looking for is a function whose derivative is e to the 2t, which means I'm looking for the antiderivative of e to the 2t. So the differential equation is just a different spin on the antiderivative question. So I'll set it up in my antiderivative language, and I can then go and say, okay, I can reverse engineer e to the 2t. It's e to the 2t, but because the chain rule is going to pop out at 2, I put a 1/2 in front. There's not a real need for substitution because it's such a simple backwards chain rule. And of course my plus c. So there is the general solution. So a lot of this is much more familiar than I might think originally. It's much better and less strange than I might have originally thought. Let's just see if there's one more we should do. Since we're not in a hurry, I'm looking for simple ones. Come to me, simple one. It does not want to come to me. I want to make one more. It'd be nice if there is one. There is not. All right, we'll make one. We will just make our own. Let's take dy dx again. Let's multiply it by x, and let's subtract an x, and then we equal x cubed. There we go. Nice. Now, in this form, it looks much worse than it is. If I isolate dy dx, it's going to be much better. So I could say, let's isolate the dy dx term to get x cubed plus x, and then we divide throughout by x to get dy dx equal to x squared plus 1. Of course, I have to divide throughout. And then I see, okay, well, this is just an antiderivative question again. I have a function y whose derivative is x squared plus 1. Therefore, y is the indefinite integral, or the antiderivative, of x squared plus 1, which I can do. It's x cubed to the 1/3 plus x, of course, plus a c, and there's my general solution. There's no reason why this has to be difficult, to be honest, because It just puts an equation solving face on something that I've been doing for a week now. All right, so let me just find my 3 examples that we did. And let's put them in a row here at the bottom. So my first example was this one. So we had dy dx equals 2x. Our simple first example equals 2x. And we had general solution y equals x squared plus c. All right. Our other example was over here at the bottom, dy dt minus e to the 2t, dy dt minus e to the 2t equals 0. Our general solution was y of t 1/2 e to the 2t plus c, which we did by our normal antiderivative procedures. And then up here we had one more example. X times dy dx minus x equals x cubed. X times dy dx minus x equals x cubed. And we found a general solution. General solution y is, what did we find? Over there, 1/3 x cubed plus x plus c. All right. There we have 3 examples for which finding the general solution was quite familiar once I understand what the equation is asking. But now you could ask, well, this isn't really a function specifically. What in particular do you want? This c can be any number. So my answer is still a little vague. You're going to have to give me some information. If I look at this first one, I'm going to make a new page just so I don't mess this one up. If I look at this first one, what is this asking? It's asking for a function that has as derivative 2x. And I found that they are basic parabolas, but shifted in a way I don't know. So if I graphed the answer, well, I don't know which one to graph. Is it the parabola that sits at 0? So for this one, c is equal to 0, because c is the vertical shift. Are you looking for this one? Ooh, little wobbly there. Which has c equal to 1, let's say. Are you looking for this one? Which has c equal to -3, perhaps. There are infinitely many. Which one do you want? You're going to have to tell me a little bit more so that I can narrow down and know which one in particular do you want. So if I'm given more information, then I can actually go a little bit further and pick exactly which one you want. Now, none of these graphs overlap. What you have to give me in the question is just a point, any point on the graph that you want, and that will then tell me, okay, it's not this one, it's not this one, it's specifically this one graph, this one function. For example, they could tell me, well, y at 2 equals 4. Some extra information. Then I can say, okay, I have a differential equation. I need to find what do these solutions look like in general. And now let's go a little bit further. Now I can say, or next, I can say, okay, let's use this extra information to find in particular which value of c, which function you want that solves the differential equation and satisfies this extra information. So I simply plug it into the original equation. Y is 4, x squared will be 2 squared plus c, and that tells me that c is 0. So then I have y as a function of x, in particular that function. And we'll call that the particular solution. So if you don't give me anything else, then really I can only stop at the general solution. But if you give me a little bit extra, then I can use that to find the particular solution. So there's a chain here. Find the general solution to the differential equation. If I'm given some more information, then I can find the particular solution. So let's do that for the other two of our 3 examples. If I go back, let's go back. I don't have a lot of space here, so let's go back to where this one was. It was over here. And let's erase this, because I'm now going to put in the extra information. So a differential equation on its own is just called a differential equation. If I'm given some extra information, like, that doesn't really matter, my function, let's say, at 0 is 1. These two together are now called an initial value problem. So in case you see somewhere they ask you, solve this initial value problem, it simply means it's a differential equation and some information extra provided. So I still go about my business finding the general solution, and now I'm going to use the extra information, plug in 1 for y and 0 for t, and e to the 0 is just 1, so that means c is 1 minus a half, so equal to 1/2. So that means my particular solution is y as a function of t, 1/2 e to the 2t plus 1/2. Now I know specifically which one. This is a solution to the initial value problem, which has the differential equation giving me my general solution and some extra information, which is just a point. Can be at 0, can be anywhere else, doesn't matter, allowing me to find the particular solution. So let's do that for our very last one, which was up here. I have a differential equation. I can go as far as the general solution unless you give me some extra information. Let's keep it nice and simple. Let's just say, let's say y at 1 equals 2. So after the differential equation, I go up here and say, next, I plug it in. So 2 for y, 1/3, 1 for x, so 1 cubed here, plus a 1 plus a c. So that means c is equal to 2 minus 1/3 minus 1. So that'll be 2/3. So my particular solution is y equals 1/3 x cubed plus x plus 2/3. So it really depends on what information is given. Regardless, I have a differential equation that is going to result in a function. That is the answer to the differential equation. And because it's linked to antiderivatives, it is going to have a c, which is really a family of answers, and we're going to call that the general solution. If they give me some extra information, then we call the differential equation paired with that extra information, we call that an initial value problem, which means I can go a little further past my general solution to find in particular which function among that family is the solution to the differential equation and that satisfies the initial value, meaning the extra information, and then we have our particular solution. So this is going to be the basic concept, even though we might make the differential equation a little bit more complicated. The idea of a general solution, particular solution, initial value problem, and all that remains the same. So for now, I would recommend you only look at the first set of questions where we are given a potential solution, and I just want to verify if that is a solution to the differential equation or not. We have to figure out how to handle more complicated differential equations, specifically ones that have x's and y's in the equation. That is going to require a new method that we will discuss the next class. Okay.